So let's go to the test preparation. The review on page 254, please. Define the following terms. So we know that experimental error is the difference between the measured and the true value. Okay? Empirical formula, simplest whole number ratio of the elements in the compound. Molecular formula is the actual number of elements in a compound. And a polyatomic ion is an ion made up of two or more atoms. Fairly simple. Okay, number 2. 3 students produce sodium nitrate using exactly the same process. The first has a percent yield of 76, the second is 104%, and the third student is 87%. Which student has the lowest experimental error? Now, how were you able to look at that and know which student had the lowest experimental error? What were you looking for?
Whichever one's closest to 100.
We're looking for whichever percentage is closest to 100, aren't we? And so with that in mind, which one was it? Good. The second one, 104%, is closest to 100. Number 3, what 2 strategies discussed in the text can be used to reduce experimental error? Tell me one, guys. What can we do to reduce experimental error? Okay, so do it very carefully. There you go.
Do it again and again.
Repeat it over and over. If you ever take a physics class, I used to teach physics, and when you do an experiment like 7 to 10 times, over and over and over, because when you repeat it over and over like that, you reduce the experimental error. You kind of get the average of what you've done. What's another way?
Have different people.
Very good. You have more than one person do the experiment. That's actually how in the real world it works. When someone discovers something, they will publish exactly what they did so that someone else can go do the experiment too and make sure that it actually works that way even when somebody else is doing it. Actually, in most places in the real world, you want to have somebody check you before you publish it because it's less embarrassing that way. But the point is that you definitely want to have someone else check it for you. Okay?
Pray before you do the experiment.
I'm sorry?
Pray before you do the experiment.
Oh, I like it. High five. Yes, that reduces error in a lot of things. Pray before you do the experiment. Okay, that's good. You knew I'd like that one, didn't you? Yes.
Ron wouldn't say it.
Oh, Ron wouldn't say it. Well, then Ron gets a high five.
Yes.
Okay. Okay. Let's go. You're wise to always think to pray before you do things?
Yeah.
Yes. I'm going to tell you another story. My youngest daughter had really, really, really bad teeth. And by the time she was 2 years old, she had 13 cavities that I could count without x-rays. So she had to have all her teeth capped. And I don't know about you, but I have a real trauma with the dentist. I mean, I just freak out at dentists, okay? Because I've had a lot of dental work, and I just freak out. And so the dentist told us she had to do all this, and I fought with her on some of the stuff. But long story short, she had to cap my daughter's teeth at 2 years old. It was like surgery, where they had to anesthetize her and do all this. And I had to work that day, teaching that day. So my husband went with her, and I dropped them both at the hospital, and I'm leaving. I mean, literally at the hospital, and I'm leaving. And I'm praying for the Lord to take care of my baby. And all of a sudden it hits me. The Holy Spirit said to me, "You never asked me if you should do this." And I go, "Lord, should I do this?" And he goes, "No." And I was like, whoa. And it was so clear, but then I could not stop it. And that was a very huge witness to me, because as I drove the hour and a half to work, I was really talking to the Lord about it. And I said, I never stopped to ask you. I just did what the doctor said. I never stopped to ask you. And it was the wrong thing to do. And when I talked to my husband and I explained it to him, he goes, "You're right. It was the wrong thing to do." You know, once we talked about it, that we actually had to borrow money to do it. And God always provides what you need. And that should have been a red flag for us, that he would provide what we needed. And once I realized we weren't supposed to do it, I started processing through what we could have done instead, and that it would have been harder on the kid, but that maybe God meant for that to be part of sanctifying her and her life, to go through that and do it step by step and slowly. And then I actually got to witness to the dentist, because I told her it was a mistake, and she goes, "What do you mean?" And I explained the whole thing to her. And she was younger than I was, and I don't think she was a Christian, but she was listening very intently, because I was explaining to her all the things God had witnessed to me, why it was the wrong thing to do, and I should have asked first. So I just want to say, even when it comes to doctors and stuff like that, become parents, don't get swept up in the moment because it's a doctor. You need to stop and pray. And the Holy Spirit will witness to your heart what you're supposed to do when you're asking Him in humility. That was a mistake. I'll tell you what, I don't do stuff like that anymore. One time was enough for me. I'll say, okay, let me pray about that. The other day I said yes to FPEA to do something, and then immediately was convicted because I didn't say, let me pray about it first. I just jumped at it and I went, Lord, I'm so sorry. Do you want me to do this? I'll go back and say no. You know? So guys, pray, ask first. It's safer. Okay, let's see. Number 4, a student heats calcium carbonate to produce calcium oxide according to the following equation, and it gives you the equation. If he starts with 100 grams of calcium carbonate and makes 45 grams of calcium oxide, what is his percent yield? Does anybody need to see that whole thing? Okay, so are you guys okay on that? Does anybody want to see that one? Or yes, okay, it's fine. That's what I'm here for, sweetie. Okay, so we have calcium carbonate, 100 grams. That's a 1 there, 100 grams. And we are trying to find out calcium oxide plus. We are trying to find out how many grams of this are produced. It says, what is the percent yield? And so to figure out the percent yield, we are going to have to know the actual, let's see. This will give us the theoretical, and then we can divide the actual by the theoretical. Are you following what I said? To find the percent yield, you have to have the actual divided by the theoretical, probably spelled that wrong, times 100. Okay, now in the problem, it actually gave us, makes, the actual yield, we're told, is 45 grams, right? We have to figure out the theoretical. That's what we have to figure out. So we come here and we go, okay, well, we have 100 grams of calcium carbonate. This is a 1-to-1 relationship, notice. So if we can find the moles of this, we can actually find the moles of the thing we're trying to go to. And so let's see, that has 100.09 grams of this to every 1 mole of this. And so that's going to give us 0.9991 moles of CaCO3. Now, like I said, that's a 1-to-1 relationship. Do you see it here? So we know that we have 0.9991 moles of CaCO. There it is. Now we need to know how many grams that is, because we're trying to fill this in. Here, Andrew, you see it? Okay. So we know with 1 mole of this, and we're going to add up calcium, which is around 40, and oxygen, which is around 16, and that's going to give us 56.08 grams. And so that's going to give us 56.03 grams of CaO. So this was the actual yield, but now we have the theoretical yield. Whoops, yeah, there you go. And so that's going to give us, and this is 2 significant figures, whereas, did they give it in 45? 45.0, shame on me. So your answer should be in 3 significant figures. Okay? Okay. Alrighty. Let's see. Let's do the next one. I should get you guys to read them. A student performs the following reaction, that she starts with 500 grams of calcium carbonate and excess iron 3 phosphate, just for J. If she ends up with a 91.1%, how many grams of calcium 3 phosphate did she end up making? Well, remember, we know that the percentage yield equals the actual over the theoretical times 100. And in this one, they have given us that she ends up with a 91.1% yield, right? And we're also told, We're not told anything else. Okay, good. But we have what she started with. So we have, got to come over here. I can't work over this hump, I'm sorry. We have, I know it sounds like somebody's killing that child, doesn't it?
They're fighting over the swing set.
Is that what's going on? Okay. All right, that's the part we need of that. Now, we have to find out the actual yield. She starts out with that, with an excess of that, and she ends up, okay, how many grams did she make? Guys, to figure this out, we have to find the actual yield and the theoretical yield, don't we? Okay? Well, actually, that's what we're looking for, is how much did she make? We're actually looking for the actual yield. So if we were to solve for that, we know that that is 91.1% divided by 100, so that's actually going to give us 91.9, times the theoretical yield, which will give us the actual yield, won't it? Right? So that's what we're doing. Okay. Do I need to keep going, or can you guys figure this out from there? I'm sorry? Andrew, do you need to see this one, or can you figure this one out from there? Okay, so we're good. All right, let's keep going, because I think that's pretty straightforward. I'm surprised they let her scream like that down there.
It's a
guy? I'd be so ashamed. Okay. I never let my girls scream. All right, let's see. Number 6. Which of the following is a chemical formula for a carbohydrate? Remember, a carbohydrate was CH2O, and so the only one that fits that description here is C, which if you divide that through by 7, it gives you CH2O. Number 7, which of the following is an empirical formula? And if you go through there, you see that A can't be divided out further and C can't be divided out further. On number 8, it says the ones that aren't empirical formulas, what are the empirical formulas? So for B, you can divide through by 3, so it ends up being PO3. For D, you divide through by 2, so it's HO. And for E, you divide through by 3, so it's C2H4NO2. Okay, number 9, what kind of compound can have both empirical and molecular formulas? That would be covalent. What kind of compound cannot have a molecular formula? That would be ionic. Number 10, a compound has an empirical formula of that and a molar mass of that. What is its molecular formula? For that, all you have to do is add up that C3H7NO, find its molar mass, divide the molar mass that's given there by the molecular mass that you just calculated, and that will tell you how much you have to multiply that through by to get the molecular formula. Does anybody need to see that, or are you guys okay on that? Number 11, a 15-gram sample of nitrogen is burned in excess oxygen. The result is a single gas with a mass of 49.3 grams. What is the empirical formula of the gas? Do you guys want me to start with a harder one on that? Or nah, do you want to see that one? Yeah. Okay, let's do it. Okay, so this one we're doing nitrogen and oxygen. Nitrogen, nope, we're doing nitrogen is burned in excess oxygen, okay? And it's going to produce something. Oh, why? So we're looking for that. That's what we're trying to do. Anyway, I probably shouldn't write that up there. Okay, so it results in a single gas, which we have 49.3 grams, okay, of the final product. And we have 15 grams of the nitrogen. And so that means that we have added in this how many grams of oxygen? Hang on. 34.3 grams of oxygen. Does everybody see that's the final product? That's the NXOY, and this is the nitrogen that was added in there. So if I subtract these, it's going to give me how much oxygen was added to this thing. Once you have that, then you can take this and you can go to the moles. So I'm going to go 15.0 grams of nitrogen times line 14.01. I'm pretty sure, is that what it is? 1 mole. Yep, okay. And so that's going to give us 1.07 moles of nitrogen. And then we're going to take our 34.3 grams of oxygen, find out how many moles that is, 16.00 grams to 1 mole, and that's going to be right around 2. So let's see. It's going to be 2.14 moles of oxygen. So then you're going to divide both of these by 1.07. So you're going to end up with nitrogen and 2 oxygens. That's your empirical formula. Okay? All right. Next. Yes?
Couldn't you just notice that nitrogen plus oxygen is nitrogen and oxygen, and then you would have just went to the moles?
Yeah, but you had to figure out how many grams of oxygen you had to figure out the moles. So that's all we did, really.
Yeah.
Okay? A liquid hydrocarbon, which is a molecule with just carbon and hydrogen in it, is burned in a combustion analysis. 450 grams of liquid produced 1,362.5 grams of carbon dioxide and that many grams of water. What is the empirical formula? Here, guys, you are just going to take the carbon dioxide, go to the moles, and then you're going to take the the water, go to the moles, and then you're going to take the water and multiply it by 2 because there's 2 hydrogens in every water molecule. So once you have the moles of hydrogen and the moles of carbon, you divide them both by the smallest number, and that tells you the empirical formula for that hydrocarbon. Are we okay on that one? Okay. Let's do the next one because it's a little trickier. A 200-gram sample of an unknown substance was burned in XX oxygen to produce that many grams of carbon dioxide, that many grams of water. There is no other product, so that tells us that there was oxygen possibly in the original sample, but nothing else. Let's see. In a separate experiment, a single molecule of a substance was found to have a mass of that. What is the molecular formula? Okay, so first we have to find the empirical formula, then we can figure out the molecular formula. So in this one, you're going to take the 39, I can do this, 39.3 grams of CO2, and you're going to find the moles, so it's 44.01 grams to every 1 mole, and so that's going to give you, where did I do it? Number 13, there it is. Okay, so it's 9.982 moles of carbon dioxide, which means that's how many moles of carbon we have in the original, okay? And then we take the amount of water, which is 239.3 grams of water, and times line 18.02 grams, 1 mole. And that's going to give us 13.31 moles of water. So if you multiply that by 2, it's going to give us 26.61 moles of hydrogen. And we have that many moles of carbon too. So I'm just going to write that here, 9.982 moles of carbon. Okay, so far so good. If we take both of those numbers of moles to grams, it's going to tell us that we have 119.8 grams of carbon, and we have 26.9 grams of hydrogen, which is going to give us 146.7 grams total. But we were told in 13 that we started with 200 grams of the original thing, and so if we take our 200 and we subtract out the carbon and the hydrogen, that's going to end up giving us how much oxygen there is there. And so that gives us 53.3 grams of oxygen. So we want to take that to moles. So we're going to go like this and go 16.00 grams to every 1 mole. And that's going to give us 13, 3.33 moles of oxygen. Now, over here we have the moles of carbon, the moles of hydrogen, and the moles of oxygen. Okay, we just kind of had to go around the tree to get to the grams of oxygen and then the moles of oxygen. We divide all three of those by the smallest number, which would be 3.33, and that's going to end up giving us C3H8O. I'm going to come over here. C3H8O. Now you're going to figure out what that mass is. So you're going to go 3 times 12 plus 8 times 1.01 plus 16.00. And so the mass of this thing is going to be 60.11 grams. That's the empirical formula. That's the mass. But it tells you in here that the mass is 180.33. I'm not dealing with AMUs. I'll deal with grams. And so what is that going to give us? 3. So we're going to multiply this through by 3. So we're going to have C9H24O3. And so that should be our final answer. Right? We okay with that? So he worked a couple different things into that problem, didn't he? Okay. All right. Number 14. Okay, we're good. You're going to be at lunch on time. Number 14, what is the percentage composition for each element in sodium phosphate? And so here, you're going to add it up. And I'm just going to show you because it might make it a little easier. We have 3 times the sodium, which is 22.99 grams. And then we have the phosphorus, which is 30.97 grams. There's only one of those. And then we have 4 times the hydrogen, which is 16.00 grams. And so that's going to give us an overall mass of 163.94 grams. That's for the whole molecule. Remember, this is what we're Okay, so now we take the sodium. So we have 3 times 22.99, and that's going to give us 68.97 grams over the total, which is 163.94. And then you multiply that by 100, and that's going to give us the percentage of sodium, which ends up being 42.07. etc. Everybody sees how that's done? So we're good. Okay, let's go on. Number 15, a sample of an unknown substance is decomposed and found to be 24.7 potassium, and it gives you the percentages. What's the empirical formula? And so with this one, you go ahead and find the moles of each of these by just saying, okay, well, potassium, we're going to say there's 24.7 grams, so I convert that to moles. And then for manganese, there's going to be 34.7 grams, so I'm going to make that into moles. And you just do that, and then you divide through by the smallest number of moles, and you're good. Does anybody need to see that one, or are we okay on that one? Okay. Let's see. Number 16. A 500-gram sample of an unknown substance is decomposed into 142.2 grams of magnesium, 71.2 grams of carbon, and some oxygen that escaped and could not be measured. What is the empirical formula? And so you just convert these into moles, and then you can figure out the empirical formula. You're not given the oxygen, but all you got to do is add up how many grams of the other two, subtract it from the original substance, that gives you the grams of oxygen, and then you just go to the moles.
You add up and then subtract by 500.
Right, so you add 144.2 plus 71.2, you add that up, subtract that from 500, and that tells you how much oxygen there is.
In the moles, and then you just
Right,
divide it by the least.
and then once you get everybody's moles, you divide everybody by the least, and you're good. Cool. No, it's good. That's good. I'm so happy. That's good. I worked on this chapter harder than most because it's not as straightforward as I would like, you know? So I kept trying to find a way to give you a shortcut on this, and I couldn't find one, and I'm sorry. So kind of just need to know what process he wants you to go through. Number 17, give the chemical formula for the following substances. Okay, so the first one Let's just get a piece of board going on here. The first one is potassium sulfate. Well, you look and potassium is K, and you know that's a +1. And sulfate you have memorized, and so you're going to flip-flop. And so this would end up being potassium sulfate. Strontium carbonate. Strontium is Sr, and it's a +2 metal. And carbonate is CO3 -2. So you would just lose the numbers because it's a 1-to-1 relationship. Okay, don't put the 2's there. That'll be wrong. Ammonium phosphate, ammonium NH4 +1, phosphate PO4 -3. So this one is going to get the 3. This one gets the 1. So you put your little parentheses there with your 3, and then you're done. Magnesium, which is a +2. Nitrate, which is a -1. So this gets the 1, this gets the 2. I erased those because as a student, when I left them, the student told me it was very confusing for them. So I try to erase them now. How many phosphorus and oxygen atoms are in the empirical formula of magnesium phosphate? So magnesium is +2 and phosphate is -3. So this one gets the 3, this one gets the 2. So first you have to do that. And then how many phosphate atoms are in that? 2, right. How many oxygen atoms are in that? 8. Okay, so you'd have to figure it out and then go from there. Number 19, manganese can have different charges in an ionic compound. What is the name of MnCO3? Well, what is the charge on CO3? -2. So what does this manganese have to be? +2. So this has to be manganese, Roman numeral 2, carbonate. Is everybody okay with that? It's not hard. Just need to know what you're doing. And then it says, what is wrong with the following sentence? Ionic compounds do not have physical bonds. It's ionic compounds can have physical bonds if you're looking at 2 polyatomic ions being in there, right? So the polyatomic ions would mess that statement up. Okay. Do you have any questions? Yes.
Do the amount of significant figures matter?
Hang on. Yes, significant figures do matter. Which number?
In the percent questions?
Yes, watch your significant figures. They absolutely do matter.
On the test, when we talk about the polyatomic ions or write them down, will it matter whether or not we do the parentheses?
Yes. Listen. This is a really good question.
If we distribute it?
No. When you're doing one of these, the only way that that's going to be acceptable if it's asking you the empirical formula. That's the only time that you can write these polyatomic ions not the way you've learned them, okay? Any other time that you're doing these polyatomic ions, don't distribute them. Put the little parentheses and put the subscript next to the parentheses. That's really, really important. So you guys are going to take your test, follow the syllabus, do the first half of the next chapter.